The square as the highest power, quadratic equations. In context, key civilizations: Egyptians, circa 2000 BC, Babylonians, circa 1600 BC. Field, algebra. Before, circa 2000 BC, the Berlin Papyrus records records a quadratic equation solved in ancient Egypt. After, 7th century, the Indian mathematician Brahmagupta solves quadratic equations using only positive integers. 10th century CE, Egyptian scholar Abu Kamil Suja ibn Aslam uses negative and irrational numbers to solve quadratic equations. 1545, Italian mathematician Girolamo Cardano publishes his Ars Magna, setting out the rules of algebra. Quadratic equations are those involving unknown numbers to the power of 2 but not to a higher power. They could contain x cubed. They could contain x squared but not x cubed, x1, and so on. One of the main rudiments of mathematics is the ability to use equations to work out solutions to real-world problems. Where those problems involve areas or paths of curves such as parabolas, quadratic equations have become very useful and describe physical phenomena such as the flight of a ball or a rocket. Ancient roots. The history of quadratic equations extends across the world. It is likely that these equations first arose from the need to subdivide land for inheritance purposes or to solve problems involving addition and multiplication. One of the oldest surviving examples of a quadratic equation comes from the ancient Egyptian text known as the Berlin Papyrus, circa 2000 BC. The problem contains the following information. The area of a square of 100 cubits is equal to that of two smaller squares. The side of one of the smaller squares is equal to 1/2 plus a quarter of the side of the other. In modern notation, this translates into two simultaneous equations. X squared plus y squared equals 100, or xy2 plus y4 y equals 4 y4 times y. These can be simplified to the quadratic equation y4 y squared plus y squared to 100 to find the length of a side in each square. The Egyptians used a method called false position to determine the solution. In this method, the mathematician selects a convenient number that is usually easy to calculate, then works out what the solution to the equation would be using that number. The result shows how to adjust the number to get the correct solution to the equation. For example, in the Berlin Papyrus problem, the simplest length to use for the larger of the two small squares is 4 because the problem deals with quarters. For the side of the small square, 3 is used because this length of y4 of the side of this other small square. Two squares created using these false position numbers would have areas of 16 and 9 respectively, which when added together give a total area of 25. This is only y4 of 100, so the areas must be quadrupled to match the Berlin Papyrus equation. The lengths therefore must be doubled from the false positions of 4 and 3 to reach the solution, 8 and 6. Other early records of quadratic equations are found in Babylonian clay tablets where the diagonal of a square is given to 5 decimal places. The Babylonian tablet YBC 7289 circa 1800 to 1500 to 1600 BC shows a method of working out the quadratic equation x squared equals 2 by drawing rectangles and trimming them down into squares. In the 7th century, Indian mathematician Brahmagupta wrote a formula for solving quadratic equations that could be applied to equations in the form ax squared plus bx equals c. Mathematicians at the time did not use letters or symbols, so he wrote a solution in words, but it was similar to the modern formula shown above. In the 8th century, Persian mathematician Al-Khwarizmi employed a geometric solution for quadratic equations known as completing the square. Until the 10th century, geometric methods were often used as quadratic equations were used to solve real-world problems involving land rather than abstract algebraic challenges. As pictured above, the Berlin Papyrus was copied and published by German Egyptologist Hannes Schott-Achenberg in 1900. It contains two mathematical problems, one of which is a quadratic equation. Negative solutions. Indian, Persian, and Arab scholars thus far had used only positive numbers. When solving the equation 10x squared plus 10x equals 39, they gave the solution as 3. However, this is one of two correct solutions to the problem. Negative 13 is the other. If x is negative 13, x squared is 169 and 10x equals negative 130. Adding a negative number gives the same result as subtracting its equivalent positive number, so 169 plus 100 negative 30 equals 169 minus 130 equals 39. In the 10th century, Egyptian scholar Abu Kamil Sujat ibn Aslam made use of negative numbers and algebraic irrational numbers such as the square root of 2 as both solutions and coefficients, numbers multiplying an unknown quantity. By the 1500s, mathematicians accepted negative solutions and were comfortable with surds, irrational roots, those that could not be expressed exactly as a decimal. They had also started using numbers and symbols rather than writing equations and words. Mathematicians that utilized the plus or minus symbol in solving quadratic equations. With the equation x cubed equals 2, the solution is not just the square root of 2, but x equals square root of 2. The plus or minus symbol is included because two negative numbers multiplied together make a positive number. While the square root of 2 times the square root of 2 is also 2, it is also true that the negative square root of 2 times the negative square root of 2 equals 2. In 1545, Italian scholar Girolamo Cardano published his Ars Magna, the Great Art, or the Rules of Algebra, in which he explored the problem: what pair of numbers have a sum of 10 and a product of 40? He found that the problem led to a quadratic equation which, when he completed the square, gave the square root of negative 15. No numbers available to mathematicians at the time gave a negative number when multiplied by themselves, but Cardano suggested suspending belief and working with the square root of negative 15 to find the equation's two solutions. Numbers such as the negative square root of 15 would be later known as imaginary numbers. Pictured above, the quadratic formula is a way to solve equations. By modern convention, quadratic equations include a number a multiplied by x squared, a number b multiplied by x, and a number c on its own. The illustration above shows how the formula uses a, b, and c to find the value of x. Quadratic equations often equal 0 because this makes them easy to work out on the graph. The x solutions are the points to where the curve crosses the x-axis. Politics is for the present, but an equation is for eternity. Albert Einstein. Structure of equations. Modern quadratic equations usually look like ax squared plus bx plus c equals 0. The letters a, b, c represent known numbers, while x represents the unknown number. Equations contain variables, symbols for numbers that are unknown, coefficients, constants, those that do not multiply variables, and operators, symbols such as the plus and equals sign. Terms are the parts separated by the operators. They can be a number or variable or a combination of both. The modern quadratic equation is 4 terms: x squared, bx, c, and 0. Above, this picture is of a graph of the quadratic equation y equals ax squared plus bx plus c creates a U-shaped curve called a parabola. This graph points the plots in black of the quadratic function where a equals 1, b equals 3, and c equals 2. This expresses the quadratic equation x squared plus 3x plus 2 equals 0. The solutions for x are when y equals 0 and the curve crosses the x-axis. These are -2 and -1. Parabolas. A function is a group of terms that defines a relationship between variables often x and y. The quadratic function is generally written as y equals ax squared plus bx plus c, which on a graph produces a curve called a parabola. When real, not imaginary solutions to ax squared plus bx plus c equals 0 exist, they will be the points where the parabola crosses the x-axis. Not all parabolas cut the x-axis in two places. If the parabola touches the x-axis only once, this means that there are coincident roots. The solutions are equal to each other. The simplest equation of this form is y equals x squared. If the parabola does not touch across the x-axis, there are no real roots. Parabolas prove useful in the real world because of their reflective properties. Satellite dishes are parabolic for this reason. Signals received by the dish will reflect up the parabola and be directed to one single point, the receiver. Above, the picture of parabolic objects have special reflective properties. With a parabolic mirror, any ray of light parallel to its line of symmetry will reflect off the surface to the same fixed point. Practical applications. Although they were initially used for working out geometric problems, today's quadratic equations are important in many aspects of math, science, and tech. Projectile light, for example, can be modeled with quadratic equations. An object thrown up into the air will fall back down again as a result of gravity. The quadratic function can predict projectile motion, the height of the object over time. Quadratic equations are used to mold the relationship between time, speed, and distance, and in calculations with parabolic objects such as lenses. They can also be used to forecast profits and loss in the world of business. Profit is based on total revenue minus production cost. Companies create a quadratic equation known as the profit function with these variables to work out the optimal sale prices to maximize profits.